I'm going to do 2. I'll do 2 out of the 5. You'll have 3 more to do after that. So what you really should try to do is draw the region here. So we have this integral from -1 to 1, of the integral from x squared to 1, of the integral from 0 to 2 minus 2y, some generic function f of x, y, z, dz, dy, dx. I'm going to set it up with respect to y first. Now, before we do that, can you tell me what z lies between? 0 and 2 minus 2y from the inner limits of integration. Can you tell me what x lies between? Y. So x squared and 1, and then x must lie between -1 and 1. From this information, we should be able to get the solid q that we're integrating over. So this will be positive x, positive y, positive z. All right, how about let's graph the equality given by z equals 2 minus 2y. Z equals 2 minus 2y. In the yz plane, what is that graph to be? But if it's just in the yz plane, it's a line that generates a plane, yeah, in space. So I think an easy way to graph this line would be to look at, say, the, what would the y-intercept be? What, if you plug in 0 for z, you'd get the y-intercept, right? So what would that be, 1? Okay, so I'll go out 1. And then what would the z-intercept be? Plug in 0 for y. And then I'll use my ruler tool. I think I'm only going to be interested in between those intercepts. So there's the z-intercept. There's the y-intercept. I connected the dots with that line. Now, can you imagine what the resulting plane would be if you translate that line segment parallel with the x-axis? It would, I'm going to erase it because I don't want to draw it yet, but it would look something like this. It would look like the plane is leaning against the xz plane, right? Yeah. But I don't want to draw that yet. Okay. Now, the 0 simply tells me that this was a good place to cut it off, this bottom 0 right here. This is a good place to cut it off, right? So that's all I'll say about that. How about let's draw this equality here. We know that y at the equal to part of the or equal to, we know y equals x squared. That turns out to be a parabola, right? Goes through 1, 1 and -1, 1 in the xy plane, doesn't it? So I'm going to draw that. I'll put 1 here, -1 on the x-axis there. And then let's do that in green, I guess. Try and give it some perspective. Okay, so right there, it goes through the origin. And then maybe right there. And then I'm cutting it off. For reasons that will become apparent, I'm cutting it off there at 1, 1 and -1, 1 in the xy plane. You see the y equals 1? Well, there's your reason, right? That cuts it off right there, right? Now, if you translate that generating parabola upward, do you see what you get? You get a parabolic cylinder, don't you? So the question becomes, what does it look like? What is the closed surface? And by the way, x goes from -1 to 1, which we pretty much already knew about, right? -1 to 1 from the other limits. So what solid do we get when we intersect the plane that's going to be in red from the red generating curve with the parabolic cylinder that's going to be in green from the green generating curve? What does that object look like? Yeah, like a parabolic wedge. Yeah. Now, so normally you could draw, and I'm going to erase this, but normally you could draw the parabolic cylinder by translating that generating curve up, right? And again, I'm going to erase this because it's just going to muck up the picture, right? But then where does that, it's going to stop. That cylinder is going to stop at the plane, right? The plane is the roof. Does everybody see that? Or the ceiling? The plane is the ceiling. So long story short, here's what I think it's going to look like. I think there's going to be an intersection curve with the parabolic cylinder and the plane in red that's going to lean against the XZ plane. And I think I can confidently predict then that intersection curve, it's going to have to curve. I know that this point is going to be on the intersection curve, and I know these 2 points will be on the intersection curve. So I think I can pretty confidently predict it's going to be kind of this, I don't know, the intersection curve it'll look like a parabola in space. It'll be both in the plane that's leaning against the XZ plane and on the cylindrical parabola. And so I'm going to stop I should have called it a parabolic cylinder. I'm going to stop the parabolic cylinder here. And then, of course, it goes in back, too, like that. Right? All right, so let's see. So I'll try to highlight the plane in red, because that's going to be the ceiling. Let's see if this works. If not, I'll have to erase it, but let's see if this works. Let's go to Draw, go to Highlighter, make it red. So I want to this is the plane. This is the plane Z equals 2 minus 2y. It's just cut off at the intersection curve where it meets the parabolic cylinder. And so I'm spending a lot of time on this because it's important you understand the picture, I think. That's the hardest thing is the geometry of this thing. Okay, so that guy is part of the plane that leans, it's Z equals 2 minus 2y, that leans against the XZ plane. And then it's cut off. Now, let me draw the intersection curve in black. Cut off right there. It's cut off here as well. And then, of course, the side is given by the parabolic cylinder. Does everybody see that? Okay, so now I think you have a good idea what this thing looks like. Let's set up kind of a generic template. Okay, F is whatever F is, F of X, Y, Z. I'm just going to call it F. I'm going to make dy my inner differential, so I'm going to integrate with respect to y first, and then I'm going to go, let's go dz dy, dy dz dx, rather. And the reason I put dz first is because z is kind of interchanged with y. And so when I set up the outer limits of integration, I'll think of z as being y, or being interchanged with y. So now the floor to ceiling is going sideways. But if you tilt your head, you can see it, right? Does everybody see that the floor, so let me draw in a line segment here. Hopefully you can see this. Does everybody see that the floor is going to be given by the cylinder in green? And the ceiling is going to be given by the plane in red. Is that clear? Okay, so what equation gives you that cylinder? Okay, green was the wrong color to choose. What equation gives you that cylinder? Y equals x squared. Okay, you can't have an inner limit of integration in terms of the inner variable of integration. So it makes sense to make the lower limit, so the lower limit corresponds to this end of this line segment that I've drawn. The lower limit is going to be x squared. The lower inner limit is going to be x squared. The upper limit is going to be given by the plane in red. We just have to figure out what the equation is. Well, we already know, except, I mean, this is it, except we can't have this upper limit be in terms of y. We know the equation of the plane is z equals 2 minus 2y. We just can't plug that in there because you can never have the limit be the same as the variable of integration. That doesn't make sense. So you have to solve for y in terms of z. Also, it makes sense that way because that's giving you this, really, this, if you turn your head, it's a height of the ceiling, right? in terms of y in terms of z. So it should be a y value. It's just we're writing it in terms of z. So what would we get if we solve this equation for y? Z minus 2 over negative 2, right? Which is, hopefully you can see that's the same as 2 minus z over positive 2 if you factor out the negative up top and turn things around. Everybody believe that? So I could make the upper limit of integration, inner limit, 2 minus z over 2, or I could split it up, make it 1 minus 1/2 z. Either way is fine. 2 minus z all over 2 will work. So we've got our inner limits of integration. That's one of the hard parts. Does everybody see that? Okay, now we need to figure out the limits, the middle limits of integration on z. Now, how do we do that? How do we get both sets of the other limits of integration, the middle limits and the outer limits? We project the solid into the plane defined by the outer variables of integration, the z and the x. Now, I think geometrically it's easy to see what it'll look like, but then we have to talk about how to get an equation for it. So I'm going to, whoops. So I'm going to draw r, but this time this is different. R is going to be in the xz plane. You project it down into the plane defined by the outer variables of integration, x and z. So I'm going to do that. Whoa, that's weird. I got to change that. So go to pen and then make it black. There we go. So this guy here represents x, horizontal axis x, vertical axis z. So z, you can see z is taking over the role of y. It makes it conceptually easier if you think of it that way. And then this intersection curve, that's the boundary, and then this guy also down here. Those are the boundaries on the plane in red, right? Just smush it. Smush that plane in red down, make y equal to 0, but don't, when you smush a bug, it gets wider, right? But that's not what it's like here. The region doesn't get wider. So smush that down, make y equal to 0, in other words, and you see that outer boundary up here? It looks like it's going to be a parabola, right? In fact, what's the x value is going to be when you smush like this guy down to here? What's that x value? Well, I think that was 1, and then, yeah, back here, when you smush this guy down, that'll be at -1, yeah. So, and we know that from the previous setup. So -1 to 1. And then what was this guy? What was the top of this guy at for z-wise? It was at 2, wasn't it? So 2. So you smash that guy down. This bottom guy just goes to be part of the x-axis. But this parabolic guy, or parabolic-looking guy, then I'll make it yellow, I guess. It's going to be my boundary of R. So geometrically, that was easy enough, but now the problem is we need to find the equation of that curve to come up with the middle limits of integration. That's the other hard part of the problem. So how do we do that? Well, dz dx would correspond to vertical or horizontal rectangles? Vertical rectangles, because z is taking over the role of y. So it's like dy dx. Okay, so let's get an equation of that yellow curve. We've got two equations to deal with that describe this yellow curve, or the black curve in space. We've got z equals 2, well, okay, we've got, let's see, y equals x squared, right? This guy actually describes the curve. But we also know that z has to be on that, well, we have to know, we know that any point on this face, the red face, or on the boundary has to be in this plane as well. So we know that z has to equal 2 minus 2y. So it becomes a sort of substitution method here to find the equation of that curve it was black in space, and then I turned it into yellow. Just replace y with x squared, and that should be the equation of that curve in yellow. And you get z is equal to 2 minus 2x squared. And it's that curve, whether it's in space or not. It's the thing that's changing is y. When you go from this black curve in space, this boundary curve, to what I change into the yellow curve of r, the boundary curve of r, the thing that's changing is y. It still has to be true that z is equal to 2 minus 2x squared, at least on the boundary curve anyway, right? Because the boundary curve is on both the plane in red and the parabolic cylinder in green. So that equation is independent of y, so it's not going to change. So it's got to be the equation of the curve in yellow after you smush the solid Q down into the xz plane. Okay, if you believe that, then this is good to go, isn't it? This has to describe the curve in yellow, 2 minus 2x squared. That's z. So that's going to give you the top of the rectangle, and then at the bottom of the rectangle is just 0. So we get 0 to 2 minus 2x squared. And then what does x run from? -1 to 1. Okay? The other one you get is almost free. There's not a whole lot of work to do. If you keep dy first, but then make it dx, dz, you just switch to not vertical rectangles, but horizontal. But that means you have to solve this for this. You actually have to get two different equations. You have to solve this equation for x in terms of z, and you'll get a plus or minus because you're taking square roots when you do that. So yeah, if you go, what would it be? It would be z minus 2, right? Over -2. Well, we already did that earlier, right? -2, and then you take the square root, right? And then the minus root would be over here, wouldn't it? Okay, does that make sense? So then those would be your middle limits of integration. Think left to right on the left end and the right ends of this rectangle. So the middle limits, or the initial limits, the inner limits don't change because we didn't change the dy. But these middle limits will change from the opposite of that square root. I think I called it 2 minus z over +2 if you look above. Yeah, and then I swapped it, didn't I? Yeah, I did that just to see if you're awake. So if you factor out a negative and swap things around, I think that's what you'll get. And then what does z run from? Think low to high. 0 to, what's this value? 2. So there's 2 of them.